Okay, just to jog your memory, we were talking about Rowhammer. We're going to talk a lot about that today. And this is a fascinating topic. We've been working on this topic for 12 plus years now, and it doesn't look like it's going to end. So let's see. Again, just to jog your memory, we built a lot of infrastructure to understand this problem. We're going to give you some results from this infrastructure. It's FPGA-based infrastructure to test memory chips. And the problem was essentially read disturbance. So whenever you access a row repeatedly, you keep activating and pre-charging the DRAM bank, and which means that you apply high voltage and low voltage repeatedly to this word line, and some cells that are vulnerable in physically adjacent rows get corrupt. And this should not be happening, but it's happening because of electrical interference. And there are very interesting underlying causes of this problem that are dealt with in the device level papers, which we're not going to go into. So this is really a problem caused by the underlying fabrication devices that's really affecting the high level, let's say, algorithms and security. Another example of this full stack thinking, if you will. Okay, so I've shown you this one also yesterday. This is our original results, which showed that basically chips that are older don't exhibit this bit flip problem, but chips that are newer exhibit this problem because cells are closer to each other and cells are smaller, so they're more vulnerable to this type of failure mechanism. Okay, I've already said this, so I'm going to skip the slide. I've already said this also. Basically, you can have a bit flip caused by the lower levels of the stack, and this could have huge implications on the higher levels of the stack. And I'm going to give you some examples today about this. Okay, and this is what we had also looked at yesterday. Basically, you can write a program. Once you know this problem, you can write a program that could exercise this problem. This is a user-level code. There's nothing really special about this code. Anyone can write this code, and they can optimize this code also. And you can download this code, as I said. Well, what this does is it selects addresses X and Y such that they map to the same bank in DRAM, and it avoids the cache hits in the CPU, and it avoids the row hits in the DRAM such that it keeps activating X and Y repeatedly. That sounds good, right? And hopefully, if the chip is vulnerable, you get bit flips. Now, the interesting thing is, in this paper, we also observed that if you sandwich one row between X and Y, such that there's only one row between X and Y, and you keep doing this hammering, this is later called double-sided hammering, and that gives you a lot more bit flips, because you're causing a lot more electrical interference in a row that's sandwiched between two aggressor rows. And that makes Rowhammer much worse, actually. We'll see more of that. Okay, and as I said, this was the last slide I covered yesterday. Basically, you get bit flips in real systems, and there's, again, nothing special about Intel and AMD. There's actually a paper coming up at Unix Security that shows that you could do this on RISC-V also. So that means that RISC-V has reasonable memory controllers today, RISC-V processors. Because just to give you an idea, at the time we did this testing, we're talking about 2012, 2013, you could if you have a memory controller that obeys the standards, you could put 1.4 million activations within a refresh interval, 64 millisecond refresh intervals. And you get a bit flip. I think the best case we saw at that time was after 139 activations. 139,000 activations, sorry. 139, we're marching toward that. We'll see that soon. But so you see that if your memory controller is actually good at activating your DRAM bank, you could easily fit that many activations that are required to induce a bit flip. Now, whether or not you could do it through a user-level program is a different question. But with an FPGA, you could do it. But this is with a user-level program, essentially. Yes?
Yeah, I had a question about that because local systems have address-based randomization for security reasons. How does it work in the presence of that?
Yeah, all of those can be bypassed.
Well, let's say like if the kernel space is disabled, then you don't have admin rights, so you can't do that, and then...
Okay. You don't have what?
You don't have the admin rights to disable ASLR, and then the code...
So, okay, basically, how does this work on address-based randomization? Without going into detail, smart security people know how to break all of those. Basically, all of those mechanisms, people have reverse engineered and figured out how to essentially bypass. Not just for Rowhammer, for other security purposes also. So I think that's a very good question, basically. What happens if you have other ways of kind of randomizing things, yeah, you'll find ways. And also, in some cases, the address space randomization doesn't work. It happens like after coarse grain intervals. And you can actually launch these attacks within very fine grain intervals. So you don't even need to bypass that in many of the Rowhammer attacks, actually. But some other attacks, some other security attacks, you may need to bypass it. Okay, so I'm going to give you, tell this as a story, basically, because it's a very funny story, I think an interesting story in research. It's also an example of believing in your own research, because there are many cases where people actually didn't believe in Rowhammer, or they tried to hide it. That's another thing. But when we wrote our paper, the first people that really took up on this was serious memory testing people, right? These people test memory, they try to find errors, they try to find bit flips, and this is Passmark software. They actually write the memtest86 program, which you may have used. It's used essentially whenever you start up your system, it tests your memory. And these folks basically say, if you read, well, you cannot read it probably from far away, but they basically said Rowhammer phenomena is characterized by our research paper. And basically they said, based on this, they added a new hammer test, which was not present. That's hammer test 13. And they basically said, albeit exposed only in extreme memory access cases are most certainly real errors. And the reason they had to say this is because they started getting a lot of complaints from people saying that my DRAM is failing in hammer test 13. Why? So they didn't believe that it would be failed, but these guys had to say, they're really real errors. This is supposed to be doing this, and go read this paper, basically. I mean, it's not supposed to be doing this, of course, but it's once you know this problem, it's expected, right? It really breaks the specification in the case. And they talk about something, so if you can take a look at it. It's very interesting. In the paper, this is the first sentence from the paper, we said that memory isolation between different memory addresses is a key property of a reliable and secure or robust computing system, and access to one memory address should not have unintended side effects on other data stored in other addresses. And I think I strongly believe this still. We should really keep this invariant in our systems. But Rowhammer breaks this invariant clearly. And we said in the paper that, we wrote this program that we showed, and we said that someone can actually extend this to hijack your computer. We didn't do that. But we believe that once you have a bit flip, someone can extend it so that you can take over a system. And these good folks from Google Project Zero did exactly that. About a year later, essentially they read our paper. They were able to replicate what we found on their laptops. I'm going to talk about that. And they were able to take over the system. Okay. So this is very interesting, I think. When we wrote the paper, we didn't do that. That's a lot of work, a lot of security engineering. But there was no question in our mind that you could do a lot of harm to a system if you get a bit flip. And before I go into what they did, I should say that this sort of bit flip, if you can induce it reliably many times, and Rowhammer is that sort of bit flip, we'll talk about that, you can take over a system. You can read data you don't have access to. You can break out of virtual machine sandbox, so your virtual machine can actually be providing a sandbox, and you're not supposed to get out of it, but you can actually get out of it, and we will see that later. At the very end, there's a historical perspective here also. You can corrupt important data, for example, render ML inference useless by corrupting some important bits in your weight matrix, and people have shown that. Or you can actually steal secret data. It could be some cryptographic keys, or ML model parameters, or some data that you really don't have access to. So it really breaks not just integrity of the system, but also confidentiality of the system. And that's why this should not be happening. Yes?
Yeah. If you have introduced root of trust, that type of security, is this still a problem? I mean, okay, you can destroy the operation maybe, but not getting data out? Or?
Yeah, I guess it depends on what you mean by root of trust, but in some cases, like if you have full encryption, you may be able to figure out that this is happening. Your data may be corrupted, but people may not be able to make use of it. Yes, that's right. But you may still lose your data because of corruption, or part of your data. Okay, I'll keep going. There are a lot of very interesting papers on these topics. People have attacked like SGX using Rowhammer also, and they were able to steal some things, but I'm not going to go into every paper. So this is Google's work. They have a beautiful black hat presentation I'd recommend people to look at it. And this is copy-paste from some parts of their blog post. As I said, they basically read the paper. They actually contacted us at some point. We discussed with them. And they selected, they basically replicated this on laptops. And they built 2 attacks. One attack essentially takes over the Google native client, which is interesting, but we'll talk about that later on. And the other attack is very, very interesting. What it does is it basically, as a user-level program, it induces these bit flips, and it's able to take over the kernel, x86, 64 Linux kernels. And the way it does is, it's a beautiful attack. I have backup slides that you can go over if you're interested in that. But the basic idea is you create page table entries in memory, and you create a lot of page table entries in memory, and you try to flip bits in those page table entries using Rowhammer by essentially hammering rows next to the page table entries. And if you're able to flip the right bits, you can gain write access or modification access to the user level process's own page tables. And if the user level process has write access to its own page table, all of the virtual memory security or access control mechanisms are broken. You could do anything you want to the system, right? Because you know the page table structure. You're essentially root at that point, right? You should not gain access to your own page table or write access to your own page table at any point in time. It's a beautiful attack. They called it page table spraying. Again, the slides, longer slides are in the backup slides. If I have to go through all of these security papers, they're beautiful, but we don't have time. Okay, so later people started talking about this even more. They called it well, it was called the Rowhammer vulnerability anyway. But I like this analogy from a famous hacker on the internet. He said that Rowhammer is like breaking into an apartment by repeatedly slamming a neighbor's door until the vibrations open the door you're after. I like this one. So if you're stuck in this room for some reason, if you're locked, don't worry. Keep banging on the wall, and eventually a door may open. That's a bit flip for you. Okay, so let me go over some interesting security works. There are many interesting works, but I'm going to pick and choose some of them. This is one of the earlier works where folks from TU Graz showed that you could induce these Rowhammer attacks remotely using JavaScript on a remote server, and they can essentially gain unrestricted access to systems of website visitors. It's very interesting, sophisticated. All of these attacks are probabilistic. There's no deterministic attack. Most attacks are not deterministic anyway in the world, but these are even more probabilistic. These folks from VU Amsterdam showed that this is actually a very interesting paper where they could gain control of an Android phone. So you download this app. Their app figures out which parts of the memory are vulnerable to Rowhammer, and with this user-level program, they fool the operating system to allocate page table entries to locations that they know is vulnerable to Rowhammer, because they know actually how the operating system works. And they basically hammer those places where they can gain access through the page table attack that Google has developed. I don't know if their thing is still operational, but if you have an Android phone, you may want to try it. Back up your data before that. Yeah. So these folks, again, similar folks, showed that you could accelerate these attacks with a GPU, because GPU has very fast, high bandwidth access to DRAM, right? So you could accelerate these attacks. Again, similar folks showed that you could actually do these attacks over the network using the RDMA, Remote Direct Memory Access interface. These folks showed essentially the same thing in a different paper. They just didn't get a chance to publish it, I think. This is actually very interesting. More recently, this is 2020 we're talking about, as you can see. These folks show that even though you may not be able to gain control of a system using Rowhammer, by placing data carefully and attacking data around it, you could actually leak private data that doesn't belong to you. So you could read bits that are belonging to some security critical application, for example. You could get secret keys, you could do other things. You could read any kind of data if you know what you're doing, essentially. And this is due to data pattern dependence of Rowhammer. Some data patterns are actually much more easily flippable, and the flipping of the bits depends on what is the data that's stored in addresses that is close to the data. Okay, it's a sophisticated attack, but it is an attack and it works. Okay, more recently, well, similarly around that time, people have been looking at also neural networks, and people have been showing that you could actually flip some interesting bits in a neural network such that you could drop the accuracy of the neural network significantly. For example, there's another paper. There are a bunch of papers that look at this thing, and there are different ways of flipping the bits using Rowhammer. And these folks, for example, show that a reasonably accurate network, I wouldn't call 90% reasonably accurate, but better than 85%, let's say. But after the attack, you can get to about 10%, right? I wouldn't be driving a self-driving car that's 90% accurate, I think. That's why I said that, I made that comment. Okay. And people have actually shown these attacks can be, again, accelerated using FPGAs, etc. And then you can take out the cryptographic keys, etc. So there are a lot of interesting things. I'm going to talk about this paper later on, but industry has been developing attacks and defenses as well, especially Google and Microsoft. This is a paper from Google, another paper. Well, this is a real paper, actually. The previous one was a blog post. And there's attacks from Microsoft also. Okay, and people actually like these pictures online. These are not my pictures. Rowhammer actually attracts a lot of interesting pictures. This could be a solution to the problem, as you can see. Or this could be another attack. A different kind of Rowhammer attack. Okay, so I'm going to give you now a little bit more deeper perspective, but this is a survey that we were invited to write to TCAD some number of years ago. It covers a lot of things in Rowhammer. As you can see, it's a bit dated right now, but it still is a very good introduction to Rowhammer if you're interested in getting into this. It covers really from the device level all the way to upper algorithm and security levels. But we've also been writing more recent surveys. This is not meant to be an extended version of it, but it's a shorter description of what is happening in Rowhammer. Again, this is still outdated, as you can see. It's January 2023, because other things have happened in 2024 that we're going to talk about soon. And we also wrote retrospectives in that issue that I mentioned. If you're interested in a very short introduction to Rowhammer history, this is the thing to read, because as you can see, it's only 1.5 pages. Okay, so unless there are questions, let's talk about some understanding right now. So if you figure out a problem like this, in my opinion, you need to first understand it. And when we actually did our studies first, we didn't really, or there was not enough literature to understand this problem. So that's what we did with our infrastructure in this paper. So we actually expanded our infrastructure. This infrastructure keeps expanding these days also. And we tested a lot of modules, 129, from 3 major manufacturers, ABC, if you remember, SHM. Okay, we're going to name them later on because they will do something that deserve their naming at some point, but you'll see that soon. I'm joking, of course, right? We'll talk about DRAM manufacturing also. I empathize with the DRAM manufacturers. It's a very, very difficult process. This is something that's very difficult to prevent, but they could have been more honest about it. Let's put it that way. Okay. So, there are a lot of things that you can characterize here. I think I've already given you some of them, but let's talk about some others. This is something interesting. You have an aggressor row and you have a victim row. From the memory controller's perspective, how close are they to each other? From the physical perspective, our hypothesis was they should be adjacent. But memory controller's perspective is very different from the physical perspective, because memory controller has some logical addresses that it issues. Internally, DRAM remaps those logical addresses to different rows. For example, the reason maybe one row may be faulty and it gets remapped to some other row that's redundant, so that you don't have that fault, right? And this fault is not necessarily a Rowhammer fault, it could be a stuck-at fault. So internally, there's a lot of tricks that DRAM manufacturers play to do address mapping. There are other reasons also, but I gave you one reason. So from the memory controller's perspective, we found out that in the worst DRAM chips that suffer from Rowhammer, most of the victim and aggressor rows are logically adjacent to each other also. Okay, so that's good. Well, I'll tell you about why that's good. But there's many cases still, there is non-adjacency. And this is not very easily predictable. This means that whenever you activate a row, the logical address that you're affecting from the memory controller's perspective is, let's say, 7 addresses apart. Okay, why is this interesting? Most of the times it's adjacent. So now this is interesting because if you're trying to solve the problem using a memory controller-based defense, you know the aggressor because you're issuing an activate, but you may not know the victim. Right? The victim may be 1 apart, victim may be 3 apart, victim may be 7 apart, and we didn't do an exhaustive testing over here. It actually is even more, potentially. So it's good to start thinking about solutions. If my solution is somehow, whenever I activate a row, I do something to the victims, like refreshing the victims, we're going to talk about that. What are the victims? I may not know. I have to reverse engineer the chip. You could actually get all of this information by reverse engineering very, very carefully. It's a very tedious process, but you could do it. Not very practical to do it for every chip that's out there in every system, because it's also chip dependent. Okay, so keep this in mind. So, okay, let's talk about access interval. So one of the reasons why Rowhammer happens is you keep accessing a row many, many times. Now if you limit that access interval such that you cannot access things that frequently, a row repeatedly that frequently, you could reduce the problem. This is intuitive, right? So the allowed fastest access time at the time we tested our chips was around 52.5 nanoseconds. So you could issue one activate after another every 52.5 nanoseconds. Now we said, what happens if you actually increase that access interval? Meaning limit your accesses to DRAM. So you need to increase your access interval to 500 nanoseconds to get rid of every single bit flip we've seen. This is the error rate. This is not a good idea because remember, we were talking about memory latency. This is actually affecting memory latency immediately. This increases your latency, and we don't want to increase latency. So basically, less frequent access lead to fewer errors, but you don't want to do that across the board. You may want to do this very, very selectively. We're going to get back to that actually. We have a paper coming up at Micro this year that does it very, very carefully and selectively. Okay. But this is interesting still. And I should also say that our testing did not exercise the worst case patterns for Rowhammer. So we didn't do double-sided testing in most of our studies. Double-sided hammer makes it even worse. So this could go up to 1 microsecond, for example, right? And you don't want that. Okay, so the most interesting or the most practical lever is the refresh interval. Because this is something you can change in existing memory controllers. And this is what we studied. Basically, as you increase the refresh interval, the problem should get worse because you're having less frequent refreshes. You could fit more of these activations to induce a bit flip. As you reduce the refresh interval, you're having more frequent refreshes, so the problem should get better or solved at some point. And this is what the curve looks like from the worst chips from 3 major manufacturers. This is measured data, of course. And if you want to get rid of every single bit flip, we basically showed that you need to increase your refresh rate by 7x. Who wants that? My cell phone should not die more faster, right? Yeah, so no one wants that, clearly. And again, as I should remind you that this is not the worst case pattern. In my opinion, the worst case is much worse, and we're going to see that solution later else. But this is a solution, and this is the solution that's going to be employed in industry very immediately. Not at 7x. Okay, there are other interesting things. Data pattern I mentioned. So this data pattern on the right side actually leads to a lot more errors than this data pattern. And the main reason is the capacitive coupling between adjacent bits is much larger in this data pattern. Of course, there's a lot of encoding that happens also, but you can find out the worst case data pattern by some testing, careful testing. So later, if you are an attacker, for example, you carefully change your data pattern so that you're more successful in your attack. If you're a defender, you may want to fix this issue somehow. So all of these actually have implications from the attacker perspective as well as the defender's perspective. So it's good to keep that in mind. Okay, there are many other key observations in this original paper. We're going to add even more to them over time. But one of the observations is that cells that are victim for Rowhammer, meaning Rowhammer vulnerable cells, are not similar to cells that are victim to retention failures. Meaning, intuitively, you may think that a cell that is very leaky, meaning you need to refresh that cell much more frequently, is more vulnerable to Rowhammer. But that's not the case. Leakage mechanism goes through the access transistor, and that's a very different failure mechanism than the Rowhammer failure mechanism. So without going into the Rowhammer failure mechanism, I have actually some backup slides that you can take a look at. It really goes through the substrate. Basically, you really lose electrons through the substrate when you're activating one word line to the other word line, essentially. That's one of the mechanisms. I kind of mentioned that yesterday. Okay, errors are repeatable, which makes it a real security problem. Essentially, more than 70% of the victim cells had errors in every iteration. So you could repeat it. Actually, this number is even larger. 70% is a conservative lower bound. And then you may say, okay, error correcting codes. You may actually have error correcting codes in DRAM. Would it fix the problem? And the answer is no. We're going to see this over and over and over. Basically, simple ECC, single error correcting, double error detecting codes cannot prevent all errors because you get about 4 errors per cache line. This is our original results. We'll see much more later on. So your ECC, in the end, ECC can prevent it, yes, but your ECC needs to be strong, much stronger than what it is today. And whenever you increase the strength of your error correcting code, you have a lot more overhead in terms of capacity, for example. But we're going to get back to that because ECC is important in today's systems. Okay, I've already said double-sided hammering, though that was another result that was characterized. So if you're interested in the original paper, you can read the paper. There's a lot here, which is interesting. But that's not the end. So it's getting much worse. We're going to talk about some of these works a little bit later. We revisited Rowhammer after 6 years or so, and we found out that it's getting much worse. We also worked with industry to look at, can we actually figure out a chip is Rowhammer free? And we did a lot of work with Microsoft on this, and we couldn't find any good way of finding that. Testing is very difficult. Testing in the cloud is even more difficult. I'm not going to talk about this, but if you're interested, this is another interesting paper. We found out that Rowhammer has many other dimensions like temperature, aggressor row active time, and spatial variation. I'm going to talk about those. How you set your word line voltage affects Rowhammer vulnerability clearly, because if you're really activating a row by applying high voltage, if you reduce that voltage, you reduce the vulnerability, but there's no silver bullet, unfortunately. We look at its effects on different things. I'm going to talk about that briefly. You may ask the question, oh, what about other DRAM, right? You look at DDR3. Well, everybody showed that DDR4 is vulnerable later, DDR5 is vulnerable. There's no reason to think that HBM is not vulnerable, but we actually verified that recently with real studies on HBM chips. So this is actually interesting because everybody's crazy about building GPU-based or accelerated HBM-based infrastructure for machine learning accelerators today, right? And I think all of them are vulnerable if you look at the studies done over here. This is HBM2. So okay, I should say something, which is these are all DRAM standards. DRAM standards don't change the core DRAM array. Core DRAM array is the same as what I showed you in all of these lectures so far. You have a subarray, you connect many of these subarrays to form a bank, you connect many of these banks to form a chip, and all of these internal structures are mostly the same internally. They just change the external interface to get higher bandwidth, for example, 3D stacking, etc., different ways of handling voltage, etc., and low power DRAM. So internally, everything is the same. So internally, all of the DRAM standards are vulnerable to this effect. Okay, but this is an interesting study to do still. So we analyzed spatial variation, which I'm going to talk about later, perhaps. Any questions? No, I'm going to jump between solutions and studies because I think they kind of feed each other, solutions and understanding. Okay, let's talk about solutions now. Now we're talking about solutions that are in around 2014. So this problem is discovered, it's in the field, clearly it's affecting almost all the chips in the field. What kind of solutions can you have? I think you need to have two types of solutions. One is immediate. Immediately, what can you do? Because you need to protect the vulnerable chips in the field. And you have limited possibilities here unless you did what we described yesterday, right? You kind of foresaw the consequences before, and you designed a memory controller that's easily reconfigurable and changeable, such that you could actually fix this with low overhead. I think that should be the future, going into the future. We should have these memory controllers that can adapt, that we can basically update in the field, just like we do software patches, right? We cannot patch hardware very well today, especially on the memory side. CPU side, you can do microcode patches, etc. But on the memory side, we don't have much patching capability. So we don't, so this is going to be very limited. But longer term, I think you can actually, this is the area of creativity, and a lot of people have developed a lot of interesting solutions, and these solutions keep coming right now. So there's a wider range of protection mechanisms. In our original paper, we discussed 7 solutions. Actually, one of the solutions that's right now adopted by JEDEC is discussed and dismissed as being not so great, but I think maybe the solution became better over time. But I'm going to talk about what we proposed. But before I go into that, so what are the solution approaches? These are the general solution approaches. It's not comprehensive. There are other approaches also. Building more robust DRAM chips. Now this involves changing your substrate, changing your materials. Very expensive. Not so easy. I think, or going to some sort of more isolation between the DRAM cells. DRAM manufacturers try to do this very hard, and I commend them on that because they actually do a good job in my opinion. Even then, Rowhammer is still a big problem. Error correcting codes we already talked about. I don't think that's a good solution to the problem. One of the reasons is the cost that I mentioned, but the other reason is fundamentally, if you think about this problem, it's a very focused problem, meaning you know exactly when this will happen. If you keep activating a row many times, you'll get this error. Error correcting codes are usually good for errors that are random. You have no idea why this is happening, because so you're actually doing a very heavyweight protection redundancy. So I think it's better to solve this problem with more specialized mechanisms than general purpose mechanisms that are high overhead. Increasing the refresh rate, this is a solution. Not a good solution anymore, but we're going to talk about that. Physical isolation is interesting. So at the operating system level or the virtual machine level, what you can do is you can waste some memory and you can protect the victim rows from the aggressor rows. So what are the victim rows? Then the question becomes, what are the victim rows? Maybe security critical data is victim rows, right? And people have proposed solutions in this effect. I think this is very costly and wasteful, and some of these are not even secure. There's actually very interesting literature in security showing that physical isolation mechanisms are not secure because you have ways of bypassing them. So I think, in my opinion, we're left with two major solutions today. One is reactive refresh, and the other is proactive throttling. Reactive refresh says, whenever you activate an aggressor row many times, refresh the victim rows. Well, this requires tracking of the aggressor row somehow, and also knowledge of what are the victim rows. So tracking can be done probabilistically, as I will show you, or it could be done deterministically, or it could be done perfectly or approximately also. And these all have implications on security, etc., as we will see. So do you track every single activation that goes to every single row? Maybe costly, right? But you could, and that's the solution that's going to be implemented in 2024, 26, etc. We will see. And then what do you do with it is another question, right? Once you track the row, you maybe compare how many times it's activated to a threshold, and then you take some mitigating action, meaning refresh the victim rows. Why does this work? Because refreshing the victim rows replenishes the charge. But you need to refresh the rows at a time that's correct. Meaning if you're too late in refreshing the victim rows, you may actually lose the data in the victim rows. Okay, I spoke too much about this, but we're going to talk about that. So proactive throttling is actually a different type of solution. The idea is figure out which rows are the aggressor rows and stop accessing them. So as opposed to trying to mitigate the effects on the victim rows, don't cause the problem further so that you don't leak the data. And this is also very interesting. In my opinion, actually, in the end, we need to combine different approaches, and it's going to be interesting. Now the problem is, this is a complex trade-off space in terms of cost, power, performance, and complexity. So every solution that is actually somewhere in this space. And we're going to see some of that. Hopefully not security, but even some solutions that are proposed give up security also. So that could be part of the trade-off space also. Yes?
In terms of aggressive applications, what kind of applications would cause this that aren't malicious?
Yeah, that aren't malicious. Hold that thought. So basically, what kind of applications can cause us that aren't malicious? We're going to get back to that. At the time these studies were done, there were very few applications. Okay, maybe I'll answer it right now. So are there applications that are non-malicious that can cause this problem? And the answer is yes. Even in 2012, 2013, when we were doing these studies, we talked with many people, and there were some applications that, for example, I'll give you one example only. There are other examples that are more sophisticated due to the coherence protocol, because coherence protocol actually causes some of these hammering effects also. There's a paper from Microsoft about that in ISCA 2022. But one application, for example, you may have a lock. The lock may be uncacheable, meaning that you need to actually hold the lock inside the memory, and you may have many threads banging on the lock in the same bank, and you may actually be hammering that particular row over there. This is a very simplified view of that application, but you can see how this may be causing Rowhammer, right? Okay, so what did industry do? Industry basically increased the refresh rates. Because this is what you can do, as I said. And I like Apple's patch because they're nice, because they credit our paper, as you can see. Essentially, they said this is a known issue, and they mitigate it by increasing the memory refresh rates. They didn't say how much. Probably 2x. That's my guess. again, this is not, this closes the vulnerability. It doesn't get rid of every single error, as we have shown. And it's going to be less and less effective in future chips, as we will see soon. Okay, so our solution, our idea was, okay, Apple is not specific. Everybody did this basically. Not just Apple. Apple is nice because they're nice, as you can see. In some other aspects, they're not nice. Okay, so our solution that we advocated in the paper as the solution that's best in our opinion is probabilistic. I think it still has very good characteristics, but it doesn't scale to the technology scaling effects that Rowhammer is having right now, and we'll see that. Basically, it's probabilistic. The basic idea is very simple. After the memory controller closes a row, it activates or refreshes its neighbors with a low probability. Now this sounds nice. You need to know the neighbors, of course, and we get a good probabilistic reliability guarantee. And if you're paranoid, you can adjust the value of P, right? And you can get higher overheads, but better reliability guarantees. Now the big advantage of this is stateless. You don't need to track anything. You just flip a coin and do some sampling and figure out when you want to do this, right? And as a result, it's low power, low performance overhead, and low cost and low complexity. And this is the solution that's the lowest cost in my opinion. And people have tried to improve the solution to be even better. And there are a lot of papers on that topic. Now this could be implemented in the DRAM chip. This could be implemented in the memory controller. Both have been tried and done. In the DRAM chip, you could actually do this due to the slack in timing and refresh parameters. So you may have some slack in the timing parameter and you sneak in a refresh to an adjacent row. And manufacturers do this actually. We're going to talk about that. You could implement in the memory controller. This was our original proposal, and we proposed that memory controller should actually have information about which rows are physically adjacent. I still believe that. I still think that memory controller should be given this information, and memory controller should be designed more tightly with DRAM. And again, if you do it in the memory controller, you could actually get good results. And Intel did it in the memory controller. This is 2014, 15 or so. And this is from BIOS. It's not exactly how we envisioned it. Basically, in the BIOS, you can pick your Rowhammer solution, as you can see. It could be hardware Rowhammer protection or 2x refresh. Well, if you pick hardware Rowhammer protection, you get to another screen that basically asks you, pick your probability without giving you a whole lot of information. You got to call Intel and ask, what is this thing about? But it's essentially very similar to what I just described. If you pick your probability 1 out of 2, then every activation you do a refresh, which is bad. So it's similar to actually what we suggested. Our suggestion was 1 out of every 1024 or something like that. So this person picked it that way. So you can say that, oh, okay, I think this is actually a solution that goes in the right direction because it's making the memory controller more intelligent, right? But we have some history. We're going to talk about that. So we argued in the paper, and I still argue that, we need more intelligent memory controllers. We talked about that in the computation perspective yesterday and the previous days, but also for security, robustness, and scaling. And Intel's solution was in the right direction. So okay, I've also mentioned that one of the reasons why we argued that we need intelligent memory controllers is because we have very good example in Flash, right? I also showed you this yesterday. We did a lot of work in Flash, which partly inspired the Rowhammer work. And here you have a hugely intelligent memory controller. I don't have time to talk about Flash, but it's really fascinating. The memory controller, the Flash controller, knows every single detail about every single cell in the Flash memory chip. It knows at what voltage it is, and it changes the voltages very carefully so that you don't lose data. So there are incremental step pulse programming mechanisms, for example. There are many different ways of programming different Flash cells. But here, the memory controller is really in charge. It is able to carefully place and control charge as much as possible. Even then, there are a lot of read disturbance issues, so it needs to take action. It needs to take action such that you don't get read disturbance. So our vision was that we should really have memory controllers that are like Flash controllers, except Flash is easier because the latencies are huge to Flash chips, so you have a lot more time in the controller to make decisions. In DRAM, I believe we need to increasingly have a DRAM translation layer going into the future, and we need to have controllers that are much more tightly coupled with DRAM. And we will see that toward the end of this lecture. Okay, so before going into more history, I think we need to understand Rowhammer even more. Many effects still need to be rigorously examined. I'm going to show you some results on some of these effects. And we still need to have better solutions to Rowhammer, more flexible, efficient, like better memory controllers, let's say. And I think co-architecting system and memory is important because we will see some of the solutions will transform the problem from bit flips to denial of service, which is probably better than bit flips. but denial of service is also something that you don't want in general in your systems. Okay. Any questions? Yes?
Sorry, maybe a bit specific, but
Yeah.
I think there's a timing parameter for DRAM for consecutive activations. How does that compare to the refresh solution?
So that was the timing parameter that I mentioned, that TRC, which is 50.
I meant FAW, the fifth activation.
Oh yeah, but that doesn't affect things because that's really across different banks. Yeah. So across different banks, this effect, at least as far as we know, doesn't happen. Yeah. Okay, so you may say that industry is actually, in my opinion, taking a right step in the right direction in 2015 or so. Intel built this memory controller, and I believe the right direction was actually to build better memory controllers. But then DRAM manufacturers came and said, we solved this problem. For DDR4, there's no more problem. And if you're told this, what do? You of course believe the DRAM manufacturers, right? And that's what everyone did. It became difficult to talk about Rowhammer because it's solved, right? Academics basically said, oh, DRAM manufacturers solved this problem, why are you talking about this? Well, of course, this is not just about claims, it's about data. So what we did was, we basically asked the question, are they really right? Did they really solve the problem? And we asked the question in two different ways. One is at the device level, which is, I have this device, I discovered this problem like 6 years ago, or 5 years ago, because this research started in 2018 or so actually. And the question is this problem really easily solvable, as people claim that they could do? And the answer to that was going to be no. It's not easily solvable. And then the second question is, okay, they solved the problem, they released these chips, we have these chips, let's take a look if they solved the problem. And the answer to that is going to be also no. Basically, they did not solve the problem because we were able to induce bit flips in those chips that they claimed they solved the problem. And after that point, you don't need to tell, you don't need ABC at that point, right? Because they're on record actually. We actually reference the places where they actually said they solved the problem. Okay, this study, we studied a lot more chips, like 1,500. We expand our infrastructure to be even more. And we basically showed that newer DRAM chips are much more vulnerable to Rowhammer because cells are smaller, cells are closer to each other. As expected, this problem should be worse. And there are new chips whose weakest cells fail after only 4,800 hammers. This is double-sided, so multiplied by 2, 9,600, less than 10,000 in the end. In the original work, we showed the number was more than 100,000. Okay, I'm going to skip this part over here, but we also showed that existing mitigation mechanisms are not effective at future technology nodes. So if DRAM manufacturers came up with a mechanism, they were extremely creative and good. Because nothing published in literature could solve this problem in future nodes, let's say, or even current nodes if you're not careful. Okay, so we beefed up our infrastructure. We were able to test actually DDR3, DDR4, LPDDR, as you can see. We tested different technology nodes, yeah, I'm not going to bore you with all of these over here. I'm going to give you one result over here. So these are 3 major manufacturers, and this is the hammer count. Hammer count to induce the first bit flip. And this is the bit flip rate, meaning error rate that you get. So DDR4 old chips have a curve like this. In the new chips, the hammer count to induce the first bit flip shifts to the left, and the error rate also increases, which means that newer chips are clearly more vulnerable than the older chips. And that's true for all manufacturers, as you can see. We don't have chips from all manufacturers, that's why the curves are kind of weird, but the trends are the same. Okay. So what about mitigation mechanisms? This is an interesting study also. There are a lot more studies in the paper that I'm skipping over. But mitigation mechanisms are interesting. Here you have, again, HC first, which is number of hammers required to induce the first Rowhammer bit flip. Now it's kind of flipped. Going from left to right, this number reduces. So as technology scaling happens, this number goes from here all the way to here. And this is the old DDR3 chips that we tested. And we're marching from left to right, as you can see. These are real measurements, these bars over here. And at some point, if the number is 1, every activation causes a bit flip. Right? That's not good. We don't want to be in that regime. And these are the different solutions. As you can see, let me see over here. This is the increased refresh rate. And this y-axis is the normalized system performance overhead. 100 is no performance overhead. 0 is you don't make progress because you keep fixing Rowhammer. And increased refresh rate gets you closer to 0 very quickly. Para is very good most of the time, but then it starts losing performance because it causes a lot of activations, a lot of refreshes. And there are some other solutions. Even ideal solution loses performance at some point. So the question is, as if you're marching from left to right, more and more benign applications can be causing this problem. And we're in a regime where benign applications may be causing bit flips, and you get a lot of performance loss to prevent those bit flips. And I think we're getting to that regime today. Okay, so basically the takeaway from this work and some of the other works later is it's really a technology scaling problem, and finding a good solution is difficult, and will become more so. So we didn't really believe the manufacturers very much, as you can see while we were doing these studies. Okay, so this is actually interesting. These are the reported HC first values from our work. So clearly, if HC first is infinite or greater than the number of activations you can cause within a refresh interval, all is good. If HC first is equal to 1, then basically maybe DRAM technology scaling has really ended, finally. So as you can see, over time, the numbers have been reducing. This is a recent number from HBM. It's about 14K, but I should say that this is the technology node of this HBM is larger than this LPDDR4, because that's the HBM we could have access to currently. It's good to do these studies so that you can understand where you are in the vulnerability spectrum. Any questions? Okay, so let me talk about the second work that we did. So we basically questioned whether the DRAM manufacturers solved the problem, and we worked with security folks who have been working on this topic and actually developing attacks like the Android attack that I mentioned. And we used our FPGA-based infrastructure to really understand what is really implemented in DRAM chips as much as possible. So our thinking, our hypothesis was the solution that they put into the DRAM chips may work, but it looked like this. That was our hypothesis. Now we need to prove this hypothesis, right? So if you want to prevent access to that other side of the walkway, this doesn't prevent access, right? I like this picture. This is from one of my students. Yeah, so basically this trespass work, TRR S-pass work, essentially showed that the chips that are protected by TRR, this was a solution by industry, target row refresh. It's essentially added to the DDR4 standard after Rowhammer became known. And they basically, it's a very wishy-washy thing added to the standard, saying that under some conditions we refresh some target rows. And there's no information other than that. If you read the standard, it's a lot of words, but I summarized it for you, so you don't need to read maybe 10 pages. So basically, we showed that these are vulnerable, and the way we showed it was doing some reverse engineering. We reverse engineered the chips enough to understand what the mitigations are doing. And our hypothesis was that internally, DRAM chips were, they had some tables to track aggressor rows, either probabilistically or deterministically. And we wanted to overflow those tables so their tracking is wrong. And if you overflow those tables and their tracking is wrong, you could cause a bit flips, essentially, right? And to overflow those tables, we started hammering many rows, as opposed to only 2 rows, right? So to be able to do this, we reverse engineered things using our FPGA-based infrastructure, and there's an automatic tool associated with it that you can download. Okay, so these are some many-sided patterns. So this is a 2-sided Rowhammer, double-sided. Red rows are the aggressor rows, blue rows are the victim rows. This is assisted double-sided or 3-sided. This is 4-sided. You could go up to 19, 20, 30, 40-sided. There's a trade-off, of course, right? As you increase the number of rows that you hammer, you do fewer hammers within a refresh interval per row. Okay. And you can see that these are real results from real chips. In some chips from one of the manufacturers, you need to do 5 hammerings to get a bit flip. In some other chips, you need to do 7 or you need to hammer 7 rows. Here, you need to hammer 9 rows, for example. So it's really dependent on the chip and the manufacturer and how well you can reverse engineer things. But it is possible to do it. And we declared victory after showing bit flips in all 3 manufacturers, not necessarily all chips, right? We said it was enough to actually show bit flips in 3 manufacturers as opposed to all chips, because we were pretty confident that if you could actually do bit flips, given more time, you could actually do bit flips in all chips, and you will see that soon also. But in some of these cases, you can see that you need, the best pattern is 19-sided Rowhammer. Okay, and we actually worked with the security researchers to take over a cell phone. They were experts in this, and we basically together showed that you could actually take over Google Pixel, for example, or Samsung, etc. You may be using some of these. And there are different attacks. Some of them is the root attack that I mentioned. Some of them is the encryption key attack, so you could get access to private keys. And we were able to show that you could actually do those attacks reasonably fast, in some cases like within seconds. Okay, so I've already said all of these. We believe that these results were really scratching the surface also. So if you actually put more time in it, you would, and some people actually would put more time in it. They're actually people who really want to get other people's data. They tend to be not us or academics in general. They tend to reside somewhere else. And they actually have the time to do it. So if we can do it with our limited resources as academics, other people who have a lot more resources can do it much better than us. And this was the argument. There was a DRAMSec workshop this year in June at ISCA. And Stefan Soroyu from Microsoft Research essentially emphasized this basically. There are powerful people in the world who really can do this much better than what has been shown in academic literature. Yes?
You mentioned that you could attack keys,
yes.
Security keys, but do you mean that there is applications where actually are keeping the security keys in DRAM?
Yes, that's correct, yes.
Okay,
yes. Yeah, I mean, people have also shown that you could attack SGX. You could actually extract keys from an SGX protected memory using Rowhammer.
Okay.
Yeah, even if you're not, even if you're extremely careful, you could actually lose your keys.
Okay.
Yeah. I think it's called SGX bomb or something, SGX hammer. People like different names. SGX hammer probably. Okay, so basically this paper showed that Rowhammer is still an open problem and security by obscurity is likely not a good solution. And I still believe that. I think we should be much more open about things. DRAM manufacturers like resorting to obscurity, as we will see again in 2024. So we have not changed this part, but at least the solutions are getting slightly better. So these two papers together caused a lot of churn in industry. And basically people started saying that, okay, we got to solve this problem. JEDEC released these not so great two papers, white papers, let's say, that talk about, oh, we should solve this problem, etc. They started a working group again. And more recently, in April 2024, they released a new Rowhammer solution, in the standard, as we will talk about. So something is happening in industry, that's good. And this is, I think, quite fascinating for me, because I always believed in the problem, and it's good that we showed the problem more so that the industry actually finally started taking action. I'm not sure if the action is in the best way today, as we will see soon. Okay, I also said that you could uncover this TRR almost completely. So the next work, one of the next works we did was actually, can we actually do better? Can we really understand what's going on in a DRAM chip with respect to Rowhammer and refresh? And the answer is yes. This is actually a fascinating observation in my opinion. Basically, we developed a methodology to uncover the inner workings of this Rowhammer mitigation mechanism. And the idea is to use data retention failures as a side channel to detect when a row is refreshed by target row refresh. I'll give you the idea very simple. There's a lot that goes into it, but the basic idea is you figure out the retention time of a row. You can do that reliably for many rows. And you don't refresh that row long enough so that you expect to get errors in that row due to retention failures, right? If you don't refresh a row that cannot retain data for more than some number of milliseconds, if you don't refresh it for longer than that number of milliseconds, you will get bit flips. Okay. So you know this information. You can verify it, you can repeat it, etc. Now, if you do something to the DRAM chip, and if that row doesn't lose the data after that number of milliseconds, something must be going on internally in the DRAM chip. So the fact that you don't get errors in a row that you think you should get errors in, retention errors in, gives you a side channel as to something is going on inside the DRAM chip, and that something is internally DRAM chip is refreshing that row. And by carefully attacking rows around it, you can actually cause this refresh, and you can figure out exactly when a DRAM chip is refreshing rows. That's the beauty of doing security and reverse engineering research. You can treat side channels as your friend to understand what's going on also, or you can treat side channels as something that you would use to attack things, right? Okay, so that's the basic idea. Once you use that basic idea, you can craft access patterns to actually cause these bit flips, and you can also figure out what's going on, and we basically figured out what different manufacturers are doing. Again, ABC, Samsung, Hynix, Micron. The reason we were not able to say these was because there was a person from industry on the paper also, and they were not allowed to write that. Anyway, but you can see that different manufacturers have different aggressor tracking mechanism, counter-based. They're tracking 16 rows here, for example. They're implementing per bank tracking. Some of them are using sampling, they're using only one. Some of them are unknown, but it's because we didn't have enough time. At some point you got to declare victory. You cannot really have a PhD where you have to test every single DRAM chips, right? Okay, so basically that's the idea over here. And we basically showed that more than, essentially almost 100% of the rows in a DRAM bank experience at least one Rowhammer bit flip if you craft the access patterns carefully. So you could use this understanding as an attacker to bypass essentially everything. And this is another example. You could craft better access patterns to induce Rowhammer bit flips, and you could actually get up to 7 Rowhammer bit flip in an 8-byte data chunk. Again, this ECC is overwhelmed by this. You cannot really correct this many errors with existing ECC mechanisms. Okay. So let me talk a little bit about understanding. These were what happened in the industry. Now, later we started doing a lot more understanding studies. This is a paper at Micro 2021 where we really wanted to understand 3 effects: temperature, aggressor row active time, and physical location of the victim DRAM cell. We have papers that are actually expanding on all of these except temperature. So I'm going to talk about temperature. So if you understand all of these, from an attacker perspective, you can build better attacks. From a defender perspective, you can build better defenses. And that was the reason why we did it. We tested a lot of chips. This is very, very heavy testing. We really tested a lot of temperature intervals, so it takes a long time to do these tests. We have a lot of observations that I'm not going to cover. But basically, the key takeaway is, with respect to temperature, there's no clean effect. Meaning, for example, retention time. If you do the retention time studies and figure out how long a cell will retain data compared to the temperature, as temperature increases, retention time decreases exponentially. It's beautiful, and this is how you can actually predict the retention times at high temperatures. Here, there's no predictability. A Rowhammer bit flip happens in a bounded temperature range, and that bounded temperature range is different for different cells. So this is an effect that is really not fully understood. There are multiple effects going on. There are device level papers that explain it, but we're not going to talk about that. We also found out that if you keep the aggressor row active a little bit longer, as opposed to closing it right away and hammering another row, this causes more bit flips. And we're going to talk about that because this turns out to be another read disturbance mechanisms in DRAM. We didn't realize it in 2021, but we realized it later, as we will see. And also, certain physical regions of the DRAM module that's under attack are much more vulnerable. So if the attacker knows which part is much more vulnerable, meaning they can induce bit flips much faster over there, they could focus there. If the defender knows this, defender can actually make their solutions more efficient by protecting the vulnerable parts much more, right? Okay. So let me give you an idea over here. I'm not going to talk about this one because I'm going to talk about that in more detail. Let's look at the variation. So we found out, for example, that 10% of the DRAM cells are twice more vulnerable compared to 90%, the remaining 90% of the DRAM cells. Now, if you know which DRAM cells are more vulnerable, you can customize your defenses to protect the more vulnerable ones more. And we showed significant area reductions for state-of-the-art mechanisms. Which we will briefly talk about some of them. Okay, I'm not going to talk about the temperature because we still have more things to cover. And there are a lot of information on this topic. So we did more Rowhammer analysis, word line voltage. I'm going to skip this one a little bit very quickly at least, but we built more infrastructure to actually test the voltage. This quite nice infrastructure, I think. Basically, we show that reducing the word line voltage reduces the Rowhammer vulnerability, but unfortunately, it has undesirable effects like increasing the latency and reducing the retention time. So there's no silver bullet, unfortunately. You may say, okay, I reduce the word line voltage, this effect goes away, it doesn't go away. No. This is the DRAM manufacturer's problem. Internally, they have very few levers to play with, and whenever you play with one lever, you destroy something else that you're optimizing for. So DRAM manufacturing is not easy, I would say. This is the part where I really empathize with them because they're really doing a lot at the device and circuit levels, both to solve this problem and to optimize the device. The problem is they don't have a lot of freedom in fixing things, and they don't have a lot of openness in trying to fix the things. We're going to talk about the freedom part. Freedom part we can fix. Openness is a problem with the culture, I think, that needs to change over time. And also it's a problem with how we treat processing and memory, right? Memory is commodity. if it's commodity and if it cannot be, let's say, specialized, or it cannot be sold more expensively, there's cutthroat competition, and these people have very low margins, and if they have very low margins, then they're not going to be open. So, because if they're open, they're going to lose those margins, right? So there's a business aspect of this also, which is less problematic in other parts. Okay, I'm not going to talk about HBM, but HBM is as vulnerable, and we're going to talk about that later on. Now let's talk about attacks and solutions a little bit more. As I said, I'll keep switching. So as I said, industry was quite interested in this problem, especially the large-scale cloud manufacturers were very vocal after they read they were following our research, but after they read our papers in 2020, they basically said, we got to solve this problem. So they put a lot of pressure in the JEDEC to solve this problem. And internally, they were doing their own research also. This is a research it's a beautiful paper by Google. What they showed was something that was not known previously. And this is the idea over here, very quickly. This is an aggressor row. You keep activating it, victim rows get bit flips. That's Rowhammer, right? We know that. Now, this is the aggressor row. If you activate this aggressor row many times, and then if you activate this aggressor row B a little bit, maybe tens or hundreds of times, the victim gets bit flips. Now this sounds interesting, right? So there's a reason why it's interesting. One is this is called blast radius, meaning this aggressor row affects this victim row, but together they affect this victim row even worse. But the real reason this is interesting is if you activate this aggressor row many times, if you tracked it internally, you would refresh aggressor row B to solve the problem. Meaning the Rowhammer solution now becomes an attack because it induces bit flips in the victim, right? So that's very nice, I think. And this is bad because now you have to take this into account in your solution also. So this is one of the reasons why solution is very difficult going into the future. And the reason they affect internally each other is not quite well understood, but again, these substrates, DRAM is very dense, and these cells share the substrate underneath, and they actually have a lot of quick electron movement internally, and that's one of the reasons. They don't explain it in the paper. But they built an attack, and they showed that they could actually take over the system this way, yes.
You need to attack the B and C rows, like the refresh mechanism.
Exactly, internally, yes. Yes, as an attacker, you don't need to attack the B rows. That's what was said. Okay. So Microsoft also published papers. This is actually very interesting because I'm not going to go into the detail, but basically they were able to use the coherence protocol to cause bit flips in real Intel systems, I think. So they were able to also show that you could do hammering in commodity workloads, meaning non-malicious code, using this coherence-induced hammering. Now I've been involved in Rowhammer for a long time, even during the times when we were in industry, and essentially, this was known in industry in around even 2011 and 2012. But finally, researchers figured it out, which is good, which is great, because industry would never talk about it. Okay, so there are other solutions to Rowhammer. I think I like the solution. It doesn't scale to very small Rowhammer counts, but our goal in this solution was to scale as much as possible with worsening vulnerability and not change the DRAM chips as much as possible. And I'll give you the basic idea of the solution. Essentially, it's a throttling mechanism. You have an attacker hammering row A. We use hardware-based Bloom filters. How many people know about Bloom filters here? Okay, that's good. If you don't know, please learn. I don't have time to cover. But Bloom filters are essentially approximate data structures that represent set membership. You have a bit vector, and with this bit vector, you keep track of what is accessed, for example, what is activated. We have counting Bloom filters, so you can count the number of activations to different locations in the Bloom filter, which represent different rows, essentially, or row sets. It's a bit more complicated than that, but that's the idea. And this is, approximate is good because it's cheaper. But it has false positives, meaning that you may actually be throttling some row activations unnecessarily, even though they may not be causing Rowhammer bit flips. Basically, Blockhammer selectively throttles accesses from within the memory controller. If an access is going to a row that we think is going to cause bit flips to victim rows, we stop access to that row. That's the idea. And you can do this you can do this securely. You can prove the security guarantees. We also have an interface to the system software saying that, we actually have a metric here saying this thread is likely to be a Rowhammer attack. And you can inform that to the system software. And then you can take other actions. So the good part about this is all open source. You can actually download it. We have actually newer mechanisms that are open source, as we will mention. But this is compatible with commodity DRAM chips, and there's no need for proprietary information or modifications to the DRAM chips. And this is another example of an intelligent memory controller. It's actually much more intelligent right now. Okay, so we're back to solution approaches. There's more over here. So what did the industry do? Well, without going into a whole lot of other solutions, industry finally acknowledged the problem. This is 2023. We're talking about 9 years after the Rowhammer paper. SK Hynix wrote a paper. They actually explicitly say Rowhammer many times over here. And they basically said that this time they were careful. They didn't claim they solved the Rowhammer. They basically said they could reduce the probability of failure due to Rowhammer by 93.1%. There's not enough information to validate or do something about this, but the basic idea is they have intelligent memory controllers, which is a step in the right direction, I think. Basically, they added one counter per DRAM row. Every DRAM row has one counter, and they're able to increase the counter when you get an activation, and they take a mitigating action if that counter is greater than some threshold. And this is the level of detail the paper has. There's not much detail. I mean, it makes sense at a high level, but there are many things that are required to make this truly work. Meaning, how do you increment the counter? When do you actually start mitigating action? What are the mitigating actions do you take? Remember the half double effect from Google? How do you actually mitigate that? So there are many, many interesting questions here that are not answered, so it's not open completely. Samsung, okay, Samsung, after seeing SK Hynix's paper, they published a paper. Impossible to read, don't worry. Yeah. Actually, Google recently published a paper showing that this solution doesn't work. I'm going to show that paper also. This was in 2024. Yeah. So Microsoft actually has a similar solution, this Panopticon. It's, again, this is per row activation counters, and they have some interesting things over here. And their solution got pushed into JEDEC in a different way, but the basic idea is in this paper. And JEDEC actually adopted some of these solutions, these per row activation counters in the end. So this is the solution that's being standardized right now. It's optional in the standard, but everybody's going to implement it because nobody wants to fall behind. But I think it's good that people are doing it. We recently had a paper that evaluated this per row activation counter solutions, and it showed that essentially these are vulnerable to denial of service because of some things. So what they did was they increased the latencies to DRAM to solve the problem, and we don't believe that's a good solution. Increasing the latencies to DRAM actually causes problems. If some application is doing Rowhammer, for example, either benignly or attacking, benignly is worse, because it could actually make your performance tank in the end. And if you're interested, you can read this paper. And again, if you want to do Rowhammer research, we open source all of these code. It's in Ramlater 2 repository, and you can easily find it. So the state of the art is here, actually, in Ramlater 2 repository. Okay, now let me ask more questions. Let's see how much time we have. Oh, wow. And we still have 100 slides or so. Okay, I'm going to go very fast. No, but okay, it's always good to ask the question, are we now Rowhammer free in 2024 and beyond? I don't believe so. Maybe this question can be more generalized as, are we now bit flip free? And that's even worse, I think. So basically, it's always good to ask the question like this. In ISCA 2023, we published a paper that basically answered this question as yes. What if there is another phenomenon that doesn't require high row activation count? Because all of these solutions require detecting high row or reasonably high row activation counts, right? And if you don't set your solutions correctly, and if there's some other mechanism that induces a bit flip at an activation count that's lower than your threshold, you're back to square one. You're vulnerable again, right? And this work showed a different redisturbance mechanism. It's called row press. And you can, again, experiment with all of this. All of the source code is open. And actually, industry has experimented with, and they've shown that you get bit flips in real DRAM. So basically, the idea is, this is a new redisturbance phenomenon that causes bit flips in real DRAM chips. It's different from Rowhammer, I'm going to show you. We were able to actually show that using a user-level program on a real system with real DRAM chips, and we provide some effective solutions. Okay, the basic idea is this. Keeping a DRAM row open for a long time causes bit flips in adjacent rows. These don't require many row activations. In fact, in some cases, only one activation is enough. You open the row, you wait long enough, you get bit flips in adjacent rows. Very bad. So this means that you don't need to hammer the row. Now, this doesn't happen in cases that are legal, meaning you need to wait for 30 milliseconds. That's not allowed in the DRAM standard, and it's unreasonable to wait for that long, I think. But this shows fundamentally that there is some other vulnerability in the device. Okay, now let's take a look at this a little bit more. I think I already said this. We're trying to find things like this, and this is a very different thing. So Rowhammer operates this way. You keep activating a row and keeping it open as minimally as possible so that you can cause many activations. Here, row press says, oh, keep the row open for longer, and you will cause bit flips with only a much smaller number of activations. So if your mitigation mechanism detects, let's say, 10,000 activations, after 10,000 activations you refresh victim rows, it will not be able to detect this attack, right? That's the idea. Okay, so we used our infrastructure again. Now you can see the names over here, SHM. And basically, we showed that this significantly amplifies DRAM vulnerability to read disturbance and is a different underlying error mechanism. Let's take a look at the results very quickly. These are results across many chips from different manufacturers, as you can see. These are, I think this is SHM over here. This is Rowhammer over here. You keep the row open by 36 nanoseconds. If you keep the row open 70.2 microseconds, which is allowed by the standard, and there are some memory controllers that could do that, you could fool the memory controller to do that, you reduce the number of activations to induce a bit flip by 1 to 2 orders of magnitude. Yeah, and I already talked about the extreme cases. Okay, so basically, where does this put us? I'm not showing everything over here, but if your row open time is 7.2 microseconds, in some DDR4 chips, you will get bit flips after 380 activations. In some HBM chips, you get bit flips after 335 hammers. Now, think about this number. There are actually real applications that still use caches and that still benefit from caches. They can activate rows hundreds of times. So we're in the real application territory, assuming that they keep the row open, of course, right? That's an assumption over here. Okay, so this number actually goes down even more if you look at, again, allowed by the standard, 9 times refresh control, if you can keep the row open that long. Okay, very quickly, this is different from Rowhammer because it gets worse as temperature increases. There's a beautiful curve. So Rowhammer is very different. And also, it affects a different set of cells compared to Rowhammer. It behaves differently as access pattern and temperature changes. I'm not going to talk about that. But we were able to show that on a real system. In a real system, basically, you can write a program, user-level program again. And in this user-level program, we keep the row open longer by accessing different cache blocks in the same row. And if the memory controller keeps the row open, and most memory controllers, especially Intel, keep the row open so that you can exploit row buffer locality if you're accessing different cache blocks, you can keep it open for long. And this is what we observe in real systems. You get bit flips after keeping the row open for 32 cache blocks, 48, 64. These are old results. The archive version actually has a much better, more bit flips. But the fact is that you can get bit flips even though the systems are protected against Rowhammer. Rowhammer should not be able to cause bit flips over here. Okay, so how do you mitigate this? Very quickly, the key idea, well, there are many types of mitigations that you can have. You can change the DRAM. We talk about some of those mitigations. Or you can change your Rowhammer mitigations. I think you need to limit the maximum row open time so that you can exploit row buffer locality a little bit, but not destroy row buffer locality completely. Once you limit the maximum row open time, you just figure out your vulnerability. Meaning, figure out the threshold that you need to start taking mitigating actions based on that row open time. And you can do that by profiling the DRAM chips. And this needs to be done anyway. You just do it for a different row open time for DRAM chips. So this makes the solutions a little bit more costly. Now performance degradation increases, as you can see. It's low, but it still increases. So you can see now these robustness issues are affecting our performance and energy. Okay, there's many more in the paper, but you can read about that. So I believe there's more to come. We're not done yet. Okay, now we need to understand more. I need to solve these bit flips. Let's see. So we have more works recently. This is combining Rowhammer and row press. You can take a look at it. You can hide refresh latency. You can take a look at it. But this was mentioned yesterday, and I strongly believe that we need better ways of communicating between the DRAM controller and DRAM. This is a work that got rejected 6 times, and finally it's going to appear at Micro. I have no idea why it got rejected 6 times, and I have no idea why it got accepted to Micro, except the fact that I think industry is finally taking, let's say, finally thinking that this is really a good solution, I think. But the basic idea is very simple. we always argued that DRAM has no flexibility, no breathing room. We ask a lot from DRAM, but we don't give it breathing room, meaning that it cannot manage things itself, right? So we argued for self-managing DRAM over here, and the idea is give some breathing room to DRAM, meaning if the DRAM needs to do some maintenance internally, it should be able to tell the memory controller, sorry, I cannot answer your request, ask me again later. And that's the very basic, simple idea over here. That's it. I don't know why this has to be rejected 6 times, by the way, sorry. Okay, so it's very low overhead. And this way, you can do a lot of things inside DRAM. For example, Rowhammer protection. That's what we showed. For example, the refresh. Internally, you can handle the refresh. Today, memory controller needs to say DRAM do refresh. Why? DRAM should do refresh internally whenever it can, right? And it can actually optimize much better the refresh mechanism because memory controller has no idea about the cells in DRAM, whereas the DRAM manufacturer has a lot of idea about what's going on inside the DRAM. Rowhammer protection is another example of this. Memory scrubbing is another example. So that's the basic idea, and we show in this paper that you can ease the processes a lot more. You don't need to change the standard that much. For example, right now, every Rowhammer solution takes 5, 10 years because it needs to be agreed upon by everybody in JEDEC, which is hundreds of companies, a huge political process that doesn't respect science or anything. And as a result, innovation is very low. In the end, you get a Rowhammer solution after 10 years, but if you have this sort of interface to DRAM, DRAM internally changes the Rowhammer solution without anybody knowing about it. If they do a bad job, you'll figure it out, yes. But if they do a good job, it's implemented right away, immediately, in the next generation, without the DRAM manufacturer having to convince 100 other people who have different reasons to be there, right? So this is, I think, a step in the right direction. And this was part of Hasan's thesis, who graduated 2 years ago, but he published his last paper 2 years after his graduation. Okay, but this is an example of the interface that we need to change. And this is actually a really mindset issue, because I'll give you the story about the paper also, because when we said, when we wrote the paper, one of the reasons for rejection is, oh, this is not good for industry. DRAM manufacturers will never implement it. That's a very subjective comment, right? In research, we should not make subjective comments. It should be more objective. We could evaluate the solution, right, as opposed to whether you believe someone will implement it or not. Okay, anyway. Okay, we have other solutions that I'm not going to talk about over here. I will mention one thing. In this paper, where we talk about spatial variation of Rowhammer, we also show that aging affects DRAM chips. So we age DRAM chips with some method. You can read the paper for more. And normally, if Rowhammer vulnerability doesn't change with aging, the minimum, however, count to induce read disturbance or Rowhammer bit flips before aging and after aging should be equal. We should be at the x over y, x equal y curve, right? But we see that after aging, a small fraction of cells have much worse vulnerability. This means that, again, this is bad for a threshold setting, right? If you set your thresholds, assuming some vulnerability, over time, that threshold needs to change. And this is another reason why we keep arguing for flexible memory controllers that can, over time, adapt to what's happening in the field. I think this is going to be a lot worse. And this is just aging in current world, right? Think about, start thinking about radiation. We go to space, and we employ this sort of thing. It's going to be much, much worse. So in my opinion, we should really get to a mindset where this robustness thing is critical. And if we really want to live in space, we should really solve it, because I don't think we have solved this problem yet. Okay, so there's another paper that talks about throttling that I'm not going to talk about. Okay, so there's more coming up. This is actually a fascinating area, I think. These are things that I could find and I'm aware of. You can see that a variety of conferences have Rowhammer attacks, solutions, reliability physics symposium actually. Folks in Shanghai Jiaotong University were able to figure out some underlying device level effects of row press. So in the row press paper, we said that there's no work that shows this at the device level. So this phenomenon was not known at the device level, and people were inspired, and they wrote paper, it's a longer version of their paper, showing that, oh, they could actually understand what's going on, and they could understand what led to row press. This is fascinating, because normally research works from the bottom up, in the sense that you have some technology, you have some understanding, you do simulations, there are some vulnerabilities, and then higher level researchers fix those or show that they're not fixed, etc. In this case, it worked oppositely. We showed that there's a row press effect in DRAM using real chips, and people at the lower level started figuring out, oh, why is this there? Let's figure it out. And I think it's fascinating that people are doing that. And if you're interested in this, I would also recommend looking at the DRAMsec workshop. This is specifically on DRAM security, and there are a lot of Rowhammer papers, as you can see. And this is the Google paper that I mentioned. Google folks showed that Samsung's DSAC solution is vulnerable, essentially. They were able to understand the paper, that's good. Maybe they talked to Samsung. Okay. Okay, we don't have a lot of time, I think. Wow, sorry. I think I will basically say, maybe I'll go back over here. So there are a lot of other issues. Is it okay if I take a couple more minutes? Okay. I didn't expect that I would take this long. Apparently this topic is taking a lot of minutes. Basically, I think we're going to have a lot more issues. So this is just to show that Rowhammer vulnerability has become much worse, read disturbance. Other technologies are also vulnerable. There is no silver bullet, unfortunately. But we need to do more work in understanding and designing and test. So human beings have not solved the bit flips in bridges. This is Pittsburgh in 2022, where I used to live. But in computing, I think we have a lot more freedom. In bridges, we have not a whole lot of freedom. Okay. Let me give you some final thoughts very quickly, I think. Because I think this is actually very interesting. So when I talk about this problem to my colleagues at Carnegie Mellon, there's a colleague called Satya, Mahadev Satyanarayanan. He designed the Andrew file system, etc. He's a distributed systems person. And he immediately started teaching this in his class, 2014. Why? Because he said this is a Byzantine failure. How many people know about Byzantine failures here? Distributed systems people. Okay, some people, that's good. So you would agree with that probably, right? Basically, these are characterized by undetected erroneous computation. It's really the opposite of what you should do in a failure tolerant system, fail fast. Here, you have a silent data corruption, and these errors can be malicious also. So it's very difficult to detect and confine these. Do all you can do to avoid these failures, basically. And that's also, the reason it's called Byzantine failures is because of this paper by Leslie Lamport. It's the Byzantine generals problem. Again, we don't have time, but I recommend reading it. This is a very fundamental, beautiful paper. There's a lot of work going on in the dependable systems community, even right now, to implement this Byzantine fault tolerance. Okay. I should also mention this paper. This is a paper that was written in 2003, before Rowhammer, IEEE Security and Privacy. These folks did a lot of very interesting research, and what they did was they were able to take over or get out of the Java virtual machine sandbox using memory errors. How did they induce memory errors? Well, this way. They had physical access to their machine, put a lamp next to memory, and the memory had a lot of errors. You could induce a lot of memory errors this way, and they were actually able to design a probabilistic attack, which is good. Now the interesting thing is this work has had impact, but not a lot of impact, because nobody's going to go around and put this to most of the machines, right? Certainly not the data centers. I mean, your smart cards may be vulnerable, sure, but it's still a pretty probabilistic attack. So basically, Rowhammer replaced that lamp with software. And this actually caused a lot of churn in the hardware security community, because now something that's seen as impractical this way was enabled by just doing instructions, executing instructions in software. That's why I think a lot of security people start examining the problem, and there are a lot of attacks that you see right now. There are a lot of solutions, even in security conferences. So Usenix Security Conference, for example, is the Rowhammer session. IEEE Security Privacy is the Rowhammer session. And you see hardware security tracks in these security conferences today. So I like this, and I think there should be more of that. In fact, I should also say that the two of the groups that discovered Meltdown and Spectre heavily worked on Rowhammer before, and they got fascinated by it, and they asked the question, what else is lurking in hardware can we exploit? And they were able to discover Meltdown and Spectre that way, in my opinion. Okay, I think I should not take too much more time, but I should probably say this is going to get worse, and we need to do more research. But it's not the only thing. Finally, I think people have realized data corruption is in logic too. These are papers from Google and Facebook, where they show that sometimes logic in CPUs that they have in data centers get bit flips. As a result, they do erroneous computation. They destroy whatever, some database, etc. It's interesting. I'd recommend looking at it. And they have nice papers. And more recently, Alibaba has a paper that characterized it. And people actually write papers to actually fix the problem also. So silent data corruption is everywhere. Maybe I will end with this slide. So I think both memory and logic errors will become worse with technology scaling. Memory has become worse much earlier, in my opinion. And these errors will create robustness problems that could be exploited for security attacks, but also for safety problems also. And I think in the end, I will summarize it this way. We cannot afford to ignore data corruption in the end. You may think you can ignore it. If you can control it, maybe you can ignore it, but if you cannot control it, which is the case in all of these almost, you cannot ignore it. And I'll end with this. We're building the infrastructure for future. We're ignoring a lot of things, sustainability, energy, maybe sometimes performance. I don't think we should ignore any of these. So if you take away something from this course, it should probably be questioning what we ignore in our systems. The cost of our systems today is huge because we ignore a lot of things, sustainability, efficiency, and data corruption. And I think I'll end over here. I'll acknowledge my group because clearly I presented their research. And I'll acknowledge people who have funded us. And you can find all of these. I'd be happy to talk more. And I should also finish with this because I talk a lot about Rowhammer in my freshman class also. Some artistically oriented student of mine drew this picture. And you can see that I'm hammering them. But there's a good reason. I should say that there's a good reason, as you can see, right?